Modern deep neural networks deliver breakthrough performance in areas like vision and language, but training them is notoriously fragile. Slow convergence, sensitivity to learning rates, and initialization problems plague practitioners. In 2015, a simple architectural modification called batch normalization, or batch norm, revolutionized the field by making training dramatically faster and more reliable. It quickly became a default component in nearly every deep learning model. This paper, How Does Batch Normalization Help Optimization, belongs to the subfield of deep learning optimization theory. The narration will walk through the surprising failure of the standard explanation for batch norm, the discovery that its main effect is smoothing the optimization landscape, and the evidence and theory that support this new understanding. Consider training a standard VGG-style convolutional network to classify CIFAR 1-0 images. Without batch norm, the loss decreases slowly and is acutely sensitive to the learning rate. Set it too high, and the loss oscillates or explodes. Set it too low, and progress is glacial. Adding batch norm layers immediately accelerates convergence and stabilizes training against learning rate and initialization choices. The original 2015 paper by Ayoff and Segedi attributed this success to reducing internal covariate shift, meaning stabilizing the distribution of layer inputs. However, when researchers measured the actual distributions of layer activations over time, they found networks with and without batch norm had surprisingly similar distributions. If the benefit came from distributional stability, why was the measured stability so similar? To understand the paper, we need to review three foundational ideas. First, what is a batch norm layer? During training, data is grouped into mini-batches. For each neuron's activations across the batch, the layer computes the mean and variance, then normalizes each activation to have mean 0 and variance 1. It then applies learned scale parameter gamma and shift parameter beta. Second, a function is Lipschitz continuous if its value changes by at most some constant times the distance between inputs. This constant bounds the steepest possible slope. Third, beta smoothness means the gradient itself changes slowly. A small beta means the gradient at one point is a good predictor of the gradient at nearby points, which is crucial for stable gradient descent. Batch norm dramatically improves these properties. The paper tests the distributional stability explanation with a simple experiment, noisy batch norm. They add random noise with non-zero mean and non-unit variance after each normalization step, creating severe distributional instability. This noisy batch norm network performs almost identically to clean batch norm. If reducing shift were the mechanism, adding instability should break it. Next, they propose an optimization-centric definition of internal covariate shift. It measures how much a layer's gradient changes when earlier layers are updated. When they measure this, batch norm networks actually exhibit larger gradient shifts than standard networks, yet train faster. Internal covariate shift is evidently not the driver. The paper's central claim is that batch norm reparametrizes the loss landscape to make it significantly smoother. To demonstrate this, they perform line search experiments. At each training step, they compute the gradient, then take steps of varying size in that direction. In standard networks, the loss varies wildly with step size, indicating poor Lipschitzness. With batch norm, the loss changes predictably. More importantly, the Euclidean change in the gradient along the step direction shrinks dramatically, sometimes by 2 orders of magnitude. They also directly measure effective beta smoothness, that is how fast the gradient changes with distance along the optimization trajectory, and find it consistently reduced. This means gradients become far more predictive after adding batch norm. When gradients are predictive, gradient descent can take larger steps without overshooting into regions where the gradient behaves differently. This explains batch norm's well-known robustness to high learning rates. It also explains robustness to initialization, because the smoother landscape makes the initial parameter distance to good solutions less critical. Faster convergence follows directly from the ability to use consistently larger and more reliable steps. This unified explanation connects several empirical properties of batch norm that previously seemed like separate benefits. Gradient predictiveness is the key. The paper presents theory for a simplified setting, a single linear layer followed by batch norm. Theorem 1 states that the squared norm of the gradient of the loss with respect to normalized activations is bounded by gamma squared over sigma subscript, j squared times an expression that subtracts the squared mean of the gradient and the squared correlation between activations and gradients. This shows batch norm provides both additive and multiplicative reduction of the Lipschitz constant. Theorem 2 shows the quadratic term of the Hessian along the gradient direction. A measure of gradient change is also reduced under mild positivity assumptions. Lemma 5 demonstrates scale invariance. Because batch norm's output is independent of the overall scale of incoming weights, any optimum in a standard network has a corresponding optimum in the normalized network, potentially starting closer to a good solution. If the benefit stems from landscape smoothing rather than distributional control, other normalization schemes should also work. The paper tests normalizations based on LP norms, L1, L2, and L infinity. These fix the scale of activations but do not enforce zero mean or Gaussian-like distributions. All of them perform comparably to batch norm, sometimes even better for deep linear networks. They also produce similar smoothing effects. Remarkably, they create even larger distributional shift than standard networks, yet still improve training. This strongly reinforces the core conclusion. It is the reparametrization that smooths the landscape rather than the control of specific distributional moments that drives batch norm success. The paper situates itself within the history of normalization methods. It retains the original batch norm layer introduced by Eyoff and Segedy, but discards the internal covariate shift explanation. Layer normalization, which normalizes across features rather than the batch, is now understood to provide smoothing benefits without requiring batch statistics. Weight normalization decouples weight magnitude and direction, offering a different reparametrization. Self-normalizing networks, or CELU networks, use a specialized activation function to achieve similar normalized activations without explicit layers. All these methods can be understood through the lens of landscape smoothing. Each provides a different way to reparametrize the optimization, making the geometry more favorable for gradient descent. The paper makes a strong case against internal covariate shift and for landscape smoothing. However, key questions remain open. First, the study focuses entirely on training dynamics, not generalization. Batch norm often improves test accuracy, but the link between smoothing and flatter minima is only conjectured and not proven. Second, the analysis deliberately excludes residual networks, such as ResNets, because their skip connections already confer some smoothing benefits. This limits applicability to the most common modern architectures. Third, the theoretical results are derived for a single linear layer followed by batch norm, not for full deep nonlinear networks. Fourth, only first-order gradient descent is considered, leaving the interaction with adaptive optimizers like Atom unexplored. Future work aims to directly prove the causal relationship between smoothing and training speed and to design normalizations that maximize this smoothing effect.